Now, if you've looked at this hyperbola formula, x squared over a squared minus y squared over b squared equals 1, you might say, well, that looks a whole lot like the ellipse formula with a plus, but there's just a minus. But that maybe doesn't make it clear why this shape actually is the way it is. But here's sort of the essentials of why this formula makes sense for a hyperbola. First off, the vertices of the hyperbola would be at a comma 0 and negative a comma 0. And that makes sense because if you plug a in for x and 0 in for y, right, you're going to get a squared over a squared. 1 minus 0 is 1. So this point actually does make this true. Of course, if you put a minus in here and square it, that doesn't change anything at all. So it has those. But why this box? So this point, 0b, I always draw in these lines. So the box goes up A, down A, sorry, right A, left A, up B, down B. But these points, obviously, if x is 0, if this is 0, there's no way a negative sign is going to be equal to 1. So it doesn't go through this, but this box is really useful because this graph has two slant asymptotes. Okay, here are the slant asymptotes. What are those slant asymptotes? Well, a line that goes through the origin, it's just y equals the slope, rise over run, goes up b over a, so that's b over a, x. This goes down b, so we'll just write plus or minus b over ax. The plus is there, the minus is there. And if you have those, it's actually really, really handy to be able to draw a parabola. Let me just give you an idea. Okay, if you have the box, right, and you have the vertices, then all you do is you draw the slants, and then an asymptote means it's getting really close. So that gives you a really good idea of what your shape is, right? But that sort of obscures the main point, which is why on earth is that an asymptote? Why on earth should I assume as x gets really big that y should get really close to b over a times x? Well, to find an asymptote, we need to solve this equation for y, I guess. So let's see. Y squared over b squared. If you moved this over to the other side, you'd get x squared over a squared minus 1, right? So from here, I guess I should take the square root of both sides. So y over b equals plus or minus the square root of x squared over a squared minus 1. Now you might really wish, as I do too, that that square root split across a minus sign, but square roots don't split across plus or minus. Square roots do split, however, across multiplication. So what I'm going to do is I'm going to actually factor out the part that I want. Okay, so what do I want here? I want x squared and a squared to be able to be square rooted. This is x squared over a squared times 1. This other term isn't quite as convenient. What on earth times x squared over a squared would equal 1? Well, a squared over x squared. Now, see what I can do is I can move the b to the other side, multiply both sides by b. So there's a b. The square root of x squared over a squared gives you an x in the numerator, an a in the denominator. And then I have the square root of 1 minus a squared over x squared, right? Okay, so this is what I want. I want to basically say this term is 1. But what happens as x goes to infinity? Well, any constant, a squared is a constant, it doesn't grow as x grows. Any constant divided by x squared goes to 0. So what's this go to? Well, this goes to the square root of 1. The square root of 1 is 1. Doesn't change anything when I multiply by that. So that means that y gets really close to plus or minus b over ax as x goes to infinity. And that's why you have those cool slant asymptotes, and that's why this box is sort of useful for making the picture.